Hi, in this example we will study 16-bit subtraction and consider the difference between subtracting signed versus unsigned numbers, and study the problem when an error occurs and the overflow condition happens. Let's begin. We are asked to write assembly code to implement n-1000 and store the result into m, where m and n are 16-bit variables. In C, we would create a 16-bit signed variable using the short denotation. Conversely, if we added unsigned to the definition of m and n, then they would be unsigned 16-bit variables. The approach will be to first bring one number into a register, then calculate the subtraction, and thirdly, to store the result back into the variable m. When we execute the load D instruction, the 16-bit value from memory location n is copied into register D. We've selected register D because it is 16 bits and matches the size of the variable n. The subtract D instruction will subtract the constant 1000. Again, the pound sign in the instruction specifies the 1000 as a constant, and after executing this instruction, register D will contain the value n minus 1000. And the last step will be to store the result into the memory location m. And now m indeed does have the value of n minus 1000, just as required. But let's consider the problem of overflow. First, let's assume m and n are unsigned 16 bits. This means n could be any number from 0 to 65,535. For example, what would happen if n happened to equal 500 when we executed this software? The answer is because 500 minus 1000, which you know should be minus 500, since this is not an unsigned 16-bit number, an overflow occurs and the carry bit is set. We could have tested this condition using a conditional branch if carry set after the subtract instruction to look for this error. Next, let's consider what would have happened if m and n are signed 16-bit numbers. In C, we would have specified a signed variable using the short definition. Short means the number n could be any number from minus 32,768 to positive 32,767. When we take a 16-bit number and subtract another number from it, we end up with a 17-bit difference. So, we ask the question, what would have happened if n happened to have equaled minus 32,500? The answer is, when we take negative 32,500 and subtract 1,000 from it, we should have gotten the result of minus 33,500. But this number doesn't fit into this range. This number is not a signed 16-bit number. Therefore, an error occurs, overflow, and the V bit will be set. We have the option of testing for this overflow condition by using the branch vset. So after an arithmetic operation on 16-bit numbers, this branch would occur if an overflow occurs. So, in summary, we have seen a 16-bit subtraction. With 16-bit operations, we specify the variables in C using either the short or the unsigned short definition. And in an assembly language, to perform a 16-bit operation, we'll use a 16-bit register. In this case, we use register D. Conversely, if we had 8-bit variables, in C, we would have defined them as char for signed 8 bits or unsigned char for unsigned 8 bits. And in assembly language, we perform an 8-bit operation by selecting an 8-bit register. Here we've selected register A, but I could have also selected register B, which is also 8 bits. The second objective of this example was to consider unsigned versus signed operations. With an unsigned operation, we used an unsigned designation in C, and then we tested for an overflow by looking at the carry bit. With signed operations, we defined the variables with the short definition in C, and after the arithmetic operation, we looked for an overflow by testing the V bit. And the third objective of this example was to study overflow. We know that if we have a 16-bit number and we subtract another 16-bit number from it, we'll get a 17-bit difference. For example, if the numbers are unsigned, if n1 and n2 are unsigned numbers, then they exist from 0 to 65,535. And when we subtract them, the result, the difference, could be any number from minus 65,000 all the way to plus 65,000. Similarly, if n and m were signed numbers, they would exist from minus 32,000 to plus 32,000. And when we subtract them, we could get a number ranging anywhere from minus 65,000 to plus 65,000. And in both cases, if we try to store the 17-bit result back into a 16-bit variable, we have the potential for an overflow, and the result might actually be incorrect. In assembly language, we could look for this incorrect answer. If the numbers are unsigned, we look at the carry bit, and if the numbers are signed, we look at the V bit. Thank you very much.